kind of competition on that so that you can understand which ones would be used in which database or in which situation. So here, one more that is called minimum covariance determinant. Already we have seen, right? So doing that one. Already we have discussed all the detail about the code. That's why we're not going to once again for those things. Just we have changed here because yesterday we had isolation forest and today we have that is called what? That is called minimum. That is called what? That is called, see here, the minimum covariance determinant. Minimum covariance determinant. So to run minimum covariance determinant, we need to have a module. The name of the module is elliptic envelope. That's the name of the module. And now we need to have a function, and that's the name of the function, elliptic envelope. So just we have called here that submodule, and this submodule is available in sklearn.covariance package. So just we have imported that one here, and just we change here the function. The function is now elliptic envelope, and here we have given the contamination rate. And yesterday we have seen that we have given 0.03%. That's why initially we're doing the experimentation with 0.03 and looking how much the accuracy in case of minimum covariance determinant. And that one is given EE, the same thing, there is no change, right? This EE is given here to model, to train the model, to train means to learn the data. And then the same thing, the rest of the part is same, there is no change. So now we can run here the same data set. You can see here we have taken here iris data set, iris.csv, doing that one. So this one thing may be observed here. So in case of isolation forest, I cannot recall exactly. These are the pattern number. This observation 114 is treated as outlier in case of this, and 117 in case of minimum covariance determinant, and 131, 134, and 141. The same thing can be observed in case of isolation forest, whether the outliers are same or not. If they are not same, then some kind of analysis can be done. If they are same, then again some kind of analysis you can do. So here already we have here the refined database. The refined database now is having 145 rows. Now we are giving this database to the decision tree model with the similar experimental setup. We didn't change anything in the decision tree. We kept all the things same here. Just looking how much is the accuracy coming here. Still, the code is not discussed in detail. Later on, whenever turn will come, then we will discuss about the decision tree and all those things. So today here we are running now decision tree, looking how much is the accuracy. The accuracy is 0.95% here, right? So if we discard, there is no change of much accuracy, because in case of iris dataset, if you don't do any kind of outlier detection, still the accuracy is 95%. I think you can recall. We ran it several times. So now if this contamination rate is changed, say that now we have how much? This is, we have now 0.03%, right? So yesterday also we have done for 10%. So now we are making this one as a 10%, looking how much is changing now. So 10% means 15 observations were going to be treated as outliers. And these are the observations you can see here: 32, 41, 105, 106, 107, 114, like that. These are the outliers now whenever we take the 10% as outliers. So now the refined database is having how many? 135 rows, means 135 observations. Now if we take 135 observations, if we train the model, if we give it to the decision tree, then what is the output looking now here? Yeah, now the accuracy is improved here. That is 0.975, around 97%. So try to understand whenever we are applying minimum covariance determinant, if the contamination rate becomes say 10%, then we're looking that the accuracy is improving in this particular data. So you try to understand, but later we are concluding. So in this case only, right? So if the contamination rate is higher, so we're looking that the accuracy becomes higher in case of iris database. Now taking the next one is part, the local outlier factors. We discussed it in detail. So now we're going to run it. See now, because the whole code is discussed in detail, so that now we're not going to discuss about the code. Just telling you if something is new, because now this local outlier factor is a submodule which is belonging to sklan.neighbors. That's why just we invoked this submodule by this package, that is sklan.neighbors. Now the function for this local outlier factor is this here local outlier factors, and here we have given the contamination rate. So initially we have given the contamination rate 10%, looking how much is the accuracy coming in case of local outlier factors. And all the things, rest of the things remain same. There is no change. The LOF, the whole thing is stored in LOF, and LOF is given to learn the model here. Now we are running here. So if you run here, then we can see in case of LOF, now which are the outliers. Looking at here, the outliers are 13, 14, 15, 33, 41, 57, 60. So I cannot recall all the things properly, but I'm looking that some of the outliers are different than minimum covariance determinant. So whenever we are applying the different models, they are selecting the different outliers, right? So based on the calculations kind of thing. And now later we are going to analyze. So these are the things. Now the refined data set is having 135 rows, means observations. Now we're going to train the model using the decision tree. So here we have same thing. We did not change any experimental setup. So if we run, that's the accuracy is 0.95. So see here, if we use the outlier, local outlier factors, if the contamination rate is 10%, then the accuracy becomes 95%. But in case of minimum covariance determinant, when the contamination rate was 10%, the accuracy was around 97%. Now we are going to change the contamination rate here, because using 3% we didn't do in case of local outlier factors. So we made it 0.3%, means 3%. If we do this one, then these are the outliers: 15, 41, 117, 18. These are becomes the outliers. So in both cases we have seen in say 3% and also for say 10%, this 15 number outlier, 15 number pattern or 15 number observation is treated as outliers in case of LOF. So now we are running with that one. See here in the refined data set, now we're having 145 rows, means 145 observations. So if we run now, the accuracy becomes 97%. So in this case, the case is reversed. When we are discarding only 3%, then the accuracy becomes 97%. When we are discarding 10%, then the accuracy becomes 95%. This is the reverse of minimum covariance determinant. Now, why happens so? So you have to analyze each of the algorithm, what's their characteristics, and at the same time, you have to analyze the data set for which we are doing the experimentation. In this case, we are doing the experimentation for iris dataset. That's why we have to give our look into the iris dataset. What's the nature of the data? What are the characteristics? So in this case, actually, data exploration part comes here. And using this data exploration means using the different kind of statistical measure, you can analyze and you can conclude something. So one is left now. That is which one? That is one class support vector machine. So doing that one, here. So one class support vector machine submodule is stored in this package is sklearn.sbm. It's not exactly SBM, it's a modification of SBM. If you're familiar with SBM, generally SBM is a supervised learning model. But one class SBM is not a supervised learning model. You can see here, see this contamination rate is written in this case as nu equals to 0.1. Here it's not contamination, you have to write as nu because this is the syntax. And now the model is trained, the model is learned, not trained, model is learned, or you can say trained. How it is trained? Using only X train, means using only independent parameter, independent variables, only the inputs. It doesn't take the output. That's why it is unsupervised learning algorithm. So now if you run here using 10% contamination rate, then looking, so we'll get 15 outliers, and these are the outliers: 30 number observation, 40 number, 50 number observation, 22, 20, 33, like that. We have here 15 observations. These are treated as outlier in case of one class support vector machine. Again, just iterating the fact, one class support vector machine, especially from the characteristics of one class support vector machine, it is very much suitable and it is very much fit for the imbalance data set. So whenever we'll have an imbalance data set, if our objective is to detect some outliers, then we need to use one class support vector machine. So now looking here, so here in the refined data set, we're having 135 rows, 135 observations. So now if we train, then looking how much accuracy we'll get here, and try to understand the data set is totally balanced. If we talk about iris data set, it's a balanced data set because all three classes are having equal size already we have seen. So here we are doing the training, and in the training, the experimental setup remains same. There is no change. Only then we can compare. So running now with how many percents? So its mu is written, I think somewhere, yeah, 10%. If 10% is treated as outliers, then the accuracy using the one class support vector machine, that is 0.92%. One thing should be pointed out here. If we change the classifier, then the accuracy can be different. Here just we are using only decision tree, because all things are being done using decision tree. That's where we are doing the experimentation only by using decision tree. But we can change it. We can use support vector machine, neural network, KNN, net base, random forest. We can use different kind of classifiers. But here we are using only decision tree. So if it is 10%, then the accuracy is 92%. Now if we change it to 3%, then looking what happens. So making it 3%. So if it is 3%, how many outliers? 5 only. 4 here, 1, 2, 3, 4 only. So total data set 146. In this case, it is treated like that. So in the refined data set, if we apply this one, then the accuracy become how much? This is 93%. Even if the outlier percentage is only 3%, this one class support vector machine producing the accuracy with the decision tree, that is 93%. So now one thing may come in your mind, that which one is better. So by theoretically or by the characteristics of the algorithms, we can tell for in this case that this is good, for in this case this is good. But you try to understand, if you want to make a conclusion, then you have to do the experimentation in different data types, different data sets, and then you have to conclude in which kind of data sets, in which kind of outlier detection technique is working better. And you have to analyze, or you can analyze based on the experimental results. And again, one thing, this is a tunable parameter. Whenever something becomes tunable parameter, you cannot predict. See here, this contamination rate, here it is represented at nu, but we have given here 3%. It's a tunable parameter. So if something is tunable parameter, then it's very difficult to define something theoretically. The tunable parameter are optimized by experimentation, but it doesn't mean that you cannot make some kind of mathematics. Yes, you can do. If you want to deduce certain kind of mathematics, then you have to do certain kind of experimentation and certain kind of mathematics on that. Then you can devise some formula or equation, and based on that, then we can conclude something. So generally, whenever some tunable parameter is there, tunable parameter means it has to be decided by experimentation. So here we have seen 4 outlier detection technique and how they are working. So whenever you will have a project, if you are having a data set, then you can make it 1%, 2%, 3%, like that. You can see whether the output or the performance of the classifier improves or not. If the performance of the classifier is not improving or doesn't improve, then you have to stop. Then you have to conclude that in this case there is no outliers. Or again, you can use different kind of data visualization tool for the high dimensional data, so that you can observe whether in the data set there is certain kind of outliers or not. And then you can conclude that yes, because there is certain kind of outliers, and then we are going to use outlier detection technique. So here the yesterday experimentation which actually were left, we discussed about that. And today we are going to talk about, up to here, say today we are going to talk about class imbalance problem. Up to here, the things we have finished up, all the things, all the detail. And the next phase which comes, that is called class imbalance problem. So coming today with the class imbalance problem. So the first question is, what is class imbalance problem? So this kind of problem is called class imbalance problem. Already we have talked about a bit what is class imbalance problem. For your understanding and simplicity, say we are having a data set of 2 classes. One class is being represented by black dot. Another class is being represented by blue dot here. So if you count the total number of black dots, it is 20 black dots are having here. And here we are having only 10 blue dots. So if a data set is made like that, then we can say it's an imbalanced data set. Means one class overpowers another class or other classes. So this kind of situation or this kind of database is called imbalanced database. So now the question, if you're having imbalanced database, then what is the problem? So if you're having imbalanced database, then it biases towards the majority class. Means whenever we have a data set, the data set has to be trained, or some kind of machine learning classifier has to be trained with the help of that database. If the database imbalance, then the classifier biases towards the majority class. What is the meaning of biases towards the majority class? It means that after the training has been done, or after the training is completed, whenever some new parent comes to the trained classifier, then the trained classifier will have a biasness to classify the new parent towards the majority class. So whenever some new parent comes, it has a tendency that the new pattern or new example will be classified towards the majority class. So whenever we have data imbalance problem, then the classifier would be biased. So now to overcome this one, because if we have such a situation, then whichever algorithms we are going to be trained will be biased. Now fortunately we are having certain approaches here, or certain techniques by which we can handle class imbalance problem. So if we categorize the approaches, then the approaches can be classified into 3 categories, and these are sampling approach. These are the approaches, these are not techniques. Approach means how we are going to do, means whether we are going to use the height, or whether we are going to use the weight of a student to classify him. These are to classify a student, that's called approaches. Students may have a doubt that what are the differences between approaches and the techniques. Approaches mean in which approaches you are going to classify somebody, with the height or with the weight. That's called approaches. Then the techniques, you can use a different technique. So similarly, in case of class imbalance, if we divide the approaches, then we can divide the approaches in 3 categories, and these are sampling approach, algorithmic approach, and unsampling approach. What is sampling approach? So if we follow the sampling approach, then this class imbalance problem would be treated, or would be resolved by increasing or decreasing the number of sample in the database. If we increase and decrease the number of sample in the data set. And if we give a treatment, then we can say that approach is sampling approach. Now, based on increase and decrease, the sampling approach can be categorized into two categories. One is called undersampling and second one is called oversampling. These are the techniques now. So now undersampling, no, these are still approach. These are the techniques. So what is undersampling actually? When we apply undersampling, it does actually, undersampling reduces majority class instances. Is somehow, because it's a, if you see this problem, this is the imbalance problem. Somehow we have to make it balance. So we can have the two ways here. If we want to increase or decrease the samples, one of what we can do, we can reduce or decrease the sample from the majority classes, so that some kind of balanceness can be restored in the database. So whenever our objective is to reduce the majority class instances from the database, then this kind of approach is called undersampling approach. Now to implement undersampling approach, we are having number of techniques, and these are the name of the techniques. RUS, that is random undersampling technique. Tomac-link based undersampling, condense based nearest neighbor undersampling, then near miss, and different kind of undersampling techniques are there. Many recent undersamplings are there, but these are very much conventional. So whenever somebody starts with undersampling, then they need to know those things, because which our new algorithms are developed, all algorithms are based on the working principle of Tomac-link, either Tomac-link or condense or RUS. So the basic techniques which are available, we need to know if we want to understand and if we want to expand our views in undersampling. Similarly, if we talk about oversampling, so when we do oversampling, it means we are trying to increase the minority class instances. Here in this example, if we do oversampling, then instead of 10, here we can increase more number of minority classes, so that some kind of balanceness can be restored in the database. Because here in this case we're having 10, and here there are 20. So now we can increase here 10 more, so that we can make it 20, or we can increase 5 here more, then we can make it 15. So if we make it 15 and it is 20, then we can say some sort of balanceness is there in the database. So if our approach is to increase the minority instances to restore the balanceness in the database, then we can say that is oversampling method. And in oversampling method or approaches, we are having number of techniques. The first one is ROS, random oversampling technique. Then is mode, borderline is mode, safe level is mode, Erasine, and there are certain new oversampling algorithms. The Gaussian is mode and K-means is mode. It is proposed in 2017. It is proposed in 2018. So if you want to work on the oversampling technique, then you can see here K-means is mode, because it's a state of art, because it is proposed in 2018. So this is about undersampling and oversampling. Now the question, sir, which one should we say adopt, whether undersampling or oversampling? Again, we have to do certain kind of experimentation, but by roughly we can tell if the database size is small. In that case, we shouldn't do undersampling. If the database size is huge, in that case, undersampling should be used. That is roughly, still there is no evidence. And in case of oversampling, if the database size is very huge, in that case we can do, if the database is very small, in that case we need to do oversampling, so that we increase the minority class instances there. If the database size is very big, then we can do undersampling, because here we're going to reduce some of the samples. Now, what is the drawback of the undersampling here? Because by doing undersampling, we can train the model, or some kind of biasness can be restored in the database. You try to understand, in case of undersampling, we are going to drop some kind of majority instances from the database. So by the time of dropping, certain kind of useful information from the data set may be dropped. So in this case, information loss may occur in case of undersampling. Similarly, if we do oversampling, it means what? Synthetically, we are creating certain kind of data there. So if we create synthetically certain kind of data, then there is a problem of overfitting. Overfitting means what? The model can work very well in the training data, but whenever some test data will come, it will drop. The variance becomes very high. Fine. So these kind of problems can be here in case of undersampling and oversampling. So the participant, you can have any questions on that, on the working principle of undersampling and oversampling. So take 1 minute.
Any doubts, participants? You can ask in the chat box, or you can unmute yourself and directly ask.
So if not, then we can look forward in next. Here we have an algorithmic approach. This is the next approach. So here we have seen that's a sampling approach. In the algorithmic approach, what happens? See here, then we'll explain. It changes the cost function. Higher misclassification cost for the minority class is given in case of algorithmic approach. What is that actually? You try to understand. Just I have given here one boundary, right? That's called a decision boundary. So when we'll have a database, there is no decision boundary. To make you understand properly that we are having two classes, just I have given here once a boundary. Generally, whenever we train a classifier, so hypothetically, a boundary is created, and this boundary is the classifier for the database. So if we have this kind of database, then we can make this kind of decision boundary or the classifier. And this kind of problem is called linearly solvable problem. Means by a single line, by a single decision boundary, the problem can be solved. So in this case, if you apply any kind of machine learning algorithm, then it produces 100% accuracy, because the problem is linearly solvable. But you try to understand in machine learning, whichever problem is given, these are the non-linear problem. So my objective is here, just this decision boundary is created. How created? By learning the classifier. So how the classifier is learned in case of machine learning? By putting the past experiences or the historical information. So in this case, these are the information, and it's a class imbalance problem. Now, if in this class imbalance problem, if you want to make a classifier, then if we want to train a classifier, then finally the classifier will put this kind of line, right? So this line is made after training. So during training, all those patterns will come here to be to make train the classifier. So when the classifier is being trained, then the black dots come down one by one. Similarly, blue dots come one by one and train the algorithm, right? So now if we train this one, then how many times this blue dot comes? Only 10 times. How many times this black dot comes? 20 times. And a part of learning is happened whenever there is a misclassification. Because if the patterns are classified properly, then there is no learning. There is no change of weight of the algorithm. And whenever one of the instances is misclassified, then to classify it, somehow the weights are changed. So it is assumed that whenever we are having most of the patterns here, so in this case, most of the time, some of the misclassification will happen for the case of black dots. So some more number of misclassification will happen, means some more number of times this classifier would be trained by the black dots than the blue dots. Now to overcome this problem, what we can do? Whenever certain kind of misclassification happens in case of blue dots, we are going to give maximum weight, because we'll get a less number. Blue dots will get less number of time, means we'll get less chances to train the classifier than the black dots. So if the black dots will get 10 times, so blue dots may get 5 times. So whenever we are changing the weights for the black dots 1 to make a balanceness, whenever there is certain kind of misclassification due to this blue dot, the weight should be given 2, right? That's why here it is said that higher misclassification cost for the minority class should be given whenever we are going to apply algorithmic approach to treat the class imbalance problem. Probably the concept is clear. In that way, actually, the training is done. Still, we did not discuss any machine learning algorithm formally yet. But this is the way. Any question here? So therefore, whenever misclassification is happened due to this minority class, then the cost function, we should give higher misclassification cost so that some kind of balanceness can be restored in the data, in the database, or you can say data set. Is there any question? There is one more type of approach that is called ensembling approach. This approach actually combines this sampling and this algorithmic approach together, and then it trains. Then the algorithm is trained. So we are not going to talk about too much about this ensembling approach. It's a separate topic actually. But you see, there is another approach. This approach is their ensembling approach. Done? Any question?
Any questions, participants?
So now we can look over the next here. So we talked about this one. Now we are going to talk about some of the undersampling and oversampling techniques. So initially we're going to talk about undersampling technique here. So the first undersampling technique is called random undersampling technique. So this technique is under this can see here, random undersampling technique is random undersampling for the majority class. So here the objective is what? Here the objective is to reduce some of the patterns from the majority class. So whenever we use this RUS, random undersampling, randomly it picks. See, if our objective is to make say 10 here out of 20, then 10 of the instances should be discarded. So if we use a random undersampling, then randomly it picks up 10 of the data points and discard it from here. Right? Randomly. So whenever randomly some points are discarded, it means what? Certain kind of meaningful or important patterns of the observations may be discarded from the data set. So if it is discarded, then automatically the performance of the classifier, which is going to be trained by this data set, will be dropping. So that's why this random undersampling is not suitable. But we try to understand if the orientation of the data is like that. This is only if you have a data visualization only, then you can understand. If the data or the samples of the majority class are highly condensed means they are very near to each other. In such a case, we can apply random undersampling because they are very near. So if some of them is omitted from the other, much information will not be lost from the database. It is believed, right? So whenever we say the imbalance ratio, this imbalance ratio means S by L, means smaller by larger. So in this case, the ratio is how much? 0.5, because the smaller is how much? 10, and large is how much? 20. That's why the ratio is 0.5. Similarly, if we have a database where S is 500, L is 1500, if we keep 0.5, then automatically 500 large sample will be deleted, and then in the final database we'll have 100 large samples. So whenever we implement the algorithm, then we need to, because it's a tunable parameter, how much accuracy means you want to have, we have to decide. So in this case, if it is 0.5, then 500 majority samples will be removed from the majority class imbalance, majority observations. So after random undersampling, here this is called random undersampling, and we have seen that there is certain kind of drawback in random undersampling method. So to overcome this drawback, we are having number of undersampling methods. So we are coming to discuss some of them, not all. So before discussing the random undersampling method, we need to discuss some of the concept. Otherwise, you cannot understand. The concept is the distance measure. Whenever we say the distance between this pattern to this pattern, already we have seen using Pythagoras distance. But on an average, in case of machine learning, the distance which is used, that is called Euclidean distance. What is the meaning of the distance actually in say machine learning, distance between two patterns? So we try to understand by this example. Whichever distance, this is Euclidean distance or city block distance, all distances came from one distance, that is called Minkowski distance. And this is the formula of the Minkowski distance. Here we have a summation of I equals to 1 to m. M is the number of attributes of a vector, because here we are finding the distance between two vectors, and P and Q. So we are finding distance between P and Q. A vector is having number of attributes. So M represents the number of attributes. And here we have this formula, 1 by R, and here to the power R. So whenever the value of R becomes 1, then it becomes city block distance. Whenever the value of R becomes 1, then it becomes a city block distance. And here we have this equation. In this case, the value of M is 2. In this case, you see the value of M is 2. So that's why for first case this, and the second case this, because the value of R is 1. So 1, this is 1, 1, this is 1. So no power is there. So in Minkowski distance, when the value of R becomes 1, then it becomes city block distance. Similarly, when the value of R becomes 2, then it becomes Euclidean distance. Here you can see here. So this is R, and here 1 by 2. That's why it's a root over. And again, this expression is given when the value of M is 2 in Minkowski distance and the value of R is 2. So then we have this expression, and that is Euclidean distance, right? So it doesn't mean that if we apply Euclidean distance and the value of M should be 2, value of M can be anything. That is the number of attributes in a vector. But you try to understand when the value of R becomes 2, then it becomes Euclidean distance. Similarly, we can increase the value of R. So even if we increase the value of R, there won't be any changes of the final result. Unnecessarily, we will create the time complexity. That's why most of the cases, this Euclidean distance is used. Now, for your clarification, I have just taken one example here. Say we want to find the distances between first observation and the second observation. First is a vector, because this vector is represented by two coordinates, by two attributes. First one, second one, and the representation of one is shown in this table. See here, we have a first here. First is having two attributes. When M equals to 1, the value is 1. When M equals to 2, the value is 2. Similarly, for the second observation, when M equals to 1, the value is 3. When M equals to 2, the value is 2 here. Similarly, here we have a third observation. So this is when M equals to 1, this is 4. When M equals to 2, this is 1. So similarly, we have these coordinates. So if we map now in XY coordinate, then we can see these are the samples here. These are the observations. So now if we want to use city block distance to find the distances between the first and second, then how we can find here? See the formula. This is the value of the first attribute of the first item, first attribute of the second item. So here objective is to find differences between first and second. So for the first one, the first value is 3, 1, 1. That's why we have a 1 minus the value is 3. There's a 3 mode plus which one? Again mode. The value of the second attribute of the first observation 2. We have a 2 here minus here also 2, 2, and it's plus. So finally, the value is 2. So in that way, the distance between two patterns or two observations are calculated, because now the distance measure is crucial and important for further slides. So already talked about one of the undersampling method, that is random undersampling method, and we have seen that certain kind of drawback and disadvantages are there. So now we have another kind of undersampling method, and it is called Nearmiss 1. So how we can calculate Nearmiss 1? See here, those points from L are retained whose mean distance to K nearest neighbor in S is lowest. So here we have a tunable parameter, that is K. Say for an example, for this example, we're going to take the value of K equals to 3. So what we're going to find? Now we are going to find the mean distances between each of the pattern of the majority class instances in the majority region to 3 nearest neighbor. 3 because the value of K is 3. That's why, see here again, I'm reading here. Those points, keep those points from L means from large majority class instances, are retained whose mean distances to K nearest neighbor point is lowest. So if the value of K is 3, then we have to find the mean distances between A observation from the majority class instances and 3 nearest neighbor observations from the minority instances. So in this example, if we take this one, then these 3 are the nearest neighbor. Now our objective is to find the mean distances then that distance would be the distance of this sample. So how we can find, say this one is the S1 sample, and for S1 sample we are finding the mean distance now. Say this one is L1, so we have a L1 here. Say this one is L2, so we have L2 here. Say this is L3, so we have L3 here by 3, because our objective is to find mean. So mean is x1. So we found the mean when the value of k is 3 for one sample. Similarly, we need to calculate mean value for all the samples. Then we can arrange those things. Say for an example, these are the distances of the sample. This is the distance, 8 is the distance of one sample, 6 is the distance of another sample. Similarly, we have calculated the distances for 20 samples. And already we know here we'll keep the samples whose distance is lowest. That's why we arrange it in, say, ascending order. So if our objective is to keep the 50%, then we'll keep the samples whose distance is 1, whose distance is 2, whose distance is 3. Like that, the samples whose distance up to 10, we'll keep only those samples in the data set, so that we can make the balance here 0.5, because in minority means in L, mean in small, because in small s, how many we are having? We are having 5. So in L, if we keep 10, then it becomes 0.5. Similarly, so this part is over. I think in the Nearmiss one is clear. Any confusion, participant here? So in that way, we can reduce the samples from the majority part of the database. Is there any question?
Any questions, participants?
If no questions, now we're coming to the next one. That is called, it is called what? It is called Nearmiss 2. So in case of Nearmiss 2, it keeps those points from L. N means all majority class instance. That is called large. It keeps those points from L whose mean distance to the k farthest point. Because in case of Nearmiss 1, it was k nearest point, but in this case, it is said that we need to find the mean distance to the k farthest point in S is lowest. So if for each of the samples from the majority region, so if we take this sample, so these and these are the farthest point in the you can say minority region. So we need to find the distance of this one. Say this is F1. Distance of this one, say this is F2. Distance of this one, this is F3. And by 3. So this would be the mean distance now. So this is the mean distance of this sample. Similarly, we need to calculate it. We can take another one. If we take this sample, then this is the one of the farthest. This is another farthest. This is another farthest, right? So we have to find the mean of this sample also. In that way, we can calculate the distances in case of near miss. Similarly, we can calculate all the distances of all the observations. And based on this criteria, now we need to keep the number of samples. If here our objective is to keep 0.5%, then we need to keep here 14, not 10. Because now in the minority region, we are having many 1, 2, 3, 4, 5, 6, and 7. So if we want to make the ratio 0.5, then in the larger region or the majority region, we need to keep how many? We need to keep 14 samples. So here 14, not only 10, 14, up to 14 we have to check. So that is called near miss. So you try to understand here we are having two tunable parameters. One is a k is a tunable parameter, right? Similarly, you can say it's a this one. Just wait a bit, let me read this one. Similarly, here you can see we have a 0.5. This is also a kind of tunable parameter, because whenever this ratio will change, then the accuracy of the database also changes. That is near miss 2. So we have another version finally, that's a near miss 3. What is that actually? Select k nearest neighbor in L, right? means in majority instances. How many? K nearest neighbor for every point in S. Now it's saying that for every point in the minority class, we need to select K nearest neighbor from the majority instances. In this case, the sample ratio is directly controlled by K and is not separately tuned. So based on value of K, the ratio is actually tuned. In this case, we don't need to give the 0.5 means the imbalance ratio separately. For an example, say in this case, means here we need to select what would be the value of K, and the value of K automatically selects how many samples would be there from the majority class instances. See the example here. If the value of K is 3, then for each instances which are lying in the minority instances, for each instances we need to select the K nearest neighbor, means 3 nearest neighbor from the majority region. Similarly here we have selected one of the sample from the minority region. So we have chosen here 3 nearest neighbor from the majority region. So it is this, say this. Similarly, we have done for this one, this, right? Similarly, here for this one also we have done this one also we have done. Similarly, we have to select K nearest neighbor for all of the samples lying in the minority region. And finally, the observations lying in the majority region, which are the pair or which are the part of the K nearest neighbor, those samples would be kept only. So if we terminate here, only these samples will be kept and other samples will be removed from here. So if the sampling is done in this working principle, then that is called near-miss tree. In case of near-miss tree, we don't have any parameter, any options to give the imbalance ratio, whether it can be 0.5, 0.7 or 0.8, because how many samples we are going to keep, it is totally dominated and is steered up by the value of K. Any question here?
Any questions, participants?
If no question, then we're coming here. We have number of things. I'm not going to discuss all those techniques. The condensed nearest neighbor, edited nearest neighbor, repeated edited nearest neighbor, atomic link removal. It is one of the important, but it's still not going to discuss because we cannot discuss all those things. So now we are coming to oversampling. So initially, if we see the first one is called random oversampling of minority class. What is that? Because here our objective is to increase the number of observation in the minority region. So if we apply random oversampling, it means what? Randomly we can create some of the examples here. Randomly we can create some synthetic pattern here. Fine. So this method is prone to overfitting because there is no way, there is no measurement. Randomly we are putting some of the random limits. How we can put? We can make duplicates of some of the observations which are already lying in the minority region. For an example, if you want to make more 5s, then what we can do? We can make here randomly the duplicates of this one 3, duplicate of this one 2, like that. Randomly we can create. So if we create randomly, then there is no way. That's why it may be subjected or it may be prone to overfitting problem. So to overcome this random oversampling, we are having number of techniques. One of them, the basic from which number of oversampling techniques are developed and proposed, that is called SMOTE. SMOTE means what? That is synthetic minority oversampling technique. As a more sophisticated means of oversampling is synthetic minority oversampling. This oversampling technique is very much popular and conventional. So going to talk about that one, how it works actually. This is the algorithm for that. Now the objective is to oversample, means somehow we have to create the synthetic pattern in the minority region. That's the objective. So now it says that for each point P in S means what? Small, means the minority region. for each point E, for each point P in S, for each sample of this minority region, what do we need to do? Compute its K nearest neighbor in S. K nearest neighbor, right? So the K is again tunable parameter. So for an example, in this example, we have taken the value of K, that is 3. So no 2, here we have chosen 2. So randomly choose the K nearest neighbor. So we have taken one of the point and the color is orange here, and the value of K is 2. So randomly we have chosen one of them, one of the point, because we have to choose each of the point from the minority region. Say we have chosen this orange one, and the value of K is 2. So we need to take these and these neighbors now. Fine. Now randomly choose R less or equals to K. Means we have to choose a number now here. That is K, that is R. And the value of R would be less or equals to K. So for example only here, so we have taken the value of R equals to 2, because 2 less or equals to 2, the condition is satisfied. So here again we try to understand, again repeating, here again we have to choose a number, that is R, and the value of R would be less or equals to K. So in this example, we have taken the value of R, that is 2. That's why we have chosen this and this here. Then which one? After that, what we need to do? Choose a random point along the line joining P and each of the R selected neighbors. So P is which one? P is this one. Someone is making noise now. Someone is making noise now, madam, you handle.
Gagan, mute yourself. Sir, please unmute yourself. I have muted all.
Okay, fine. So now what we need to do now, we to make a line from this P, because we have chosen a point. We need to choose each of the point, and here we have chosen one of the point, and that is this orange. Now we have to make a line with all of the neighbors, R neighbor. So we have chosen here 2R. So this one and this one, this one and this one, they are connected now. So it says that now choose a random point in between this line. So we can choose any point here, here. So within this line, we can choose any of the point here. Here, just we have chosen one point. Similarly, here we have chosen one point now. So now we have chosen 2 points here. So the point should be in between this line, this and this. Just we have to choose. We can choose any of the place. So here we have chosen here. It can be chosen here also, right? So any one of them. That thing is stated here. Choose a random point along the lines joining P. P is this one, and each of the R selected neighbors. So in this case, we have chosen all the neighbors. The value of R is 2. So we have made the line, and here we have chosen this point. So now these 2 points are the synthetic points what we have created in the minority region. And finally, it said what? Add these synthetic points to the dataset with class S. So now we have added. Now we need to add this point and this point labeled as S, means minority examples or the samples. In that way, actually, smooth works. And again, in this case, we have to give this ratio 0.5, 0.6, or 0.9, 0.8 kind of thing. Now you may have a question, if we give 0.5, now if we create for each sample the 2 neighbors and create 2 kind of things, 2 synthetic pattern, then how this is possible? If it is 0.5, whenever it reaches to 0.5, then it stops the procedure. It doesn't mean that it will do for all the things, because here we have a restriction for the, and that is a threshold. Whenever it reaches, because it starts picking one of them, one from the minority, whenever the size becomes 0.55, then it stops. This is smooth. In this way, the smooth is working. It's a oversampling technique. Now we have some more versions. As stated as there are 2 enhancement versions of a smooth, and it is observed that in many cases these 2 advanced versions are working more than smooth, and these are called smooth borderline smooth 1 and borderline smooth 2. Again, I'm repeating, The smooth is having two advanced versions, and the name of these two advanced versions are borderline smooth 1 and borderline smooth 2. Because in most of the cases, it is observed that, or sometimes it is observed that these borderline smooth 1 and borderline smooth 2 work better than smooth. Now, what's the working principle of borderline smooth 1? So in borderline smooth 1, this is the algorithm. What is that? See here. For each point P in S, S means for the minority region. For the minority region, for each sample, here the sample, we have taken one of the sample, this. So for each sample, what we need to do? Compute its M nearest neighbor in T. T means what? The total data set. T means T equals to S plus L, means minority class plus majority class. So our objective here is to select M nearest neighbor. So we have to define the value of M. In this example, we have chosen the value of M equals to 4. Because here I have shown you this example, right? So for this minority instances, we have chosen 1, 2, 3, 4, 4 neighbors. That's why the value of M is 4 here, right? Up to here, the part is clear. Then all this set MP, this set MP, which set is MP? MP is the set consists of M nearest neighbor. So now MP equals to this. And now let calculate the M0. The M0 is what? M0 equals to MP. In MP set we have which one? 1, 2, 3, 4. 4 black dots. Intersection L. L means what? Majority. So all black dots comes under majority. So now if we find the intersection between this and this, then the value of M becomes 4. Because in MP already we are having all the nearest neighbor, and these are the nearest neighbor. And we are finding the intersection with L. L is the majority pattern. So in this case, the value of M0 equals to 4. Now the cases are coming here. The first case is if M0 equals to M, P is a noisy pattern, noisy example. Ignore P and continue to the next point. So you try to understand in this case, the value of M0 becomes how much? 4. And the value of M is how much? 4. That's why P is a noisy example. Actually, in case of borderline smooth, it says that the sample which is very much closely to the border, we're not going to create some synthetic pattern based on that observation. The patterns which are neither far away from the boundary, not too close the boundary, we will select this kind of patterns, and then we'll create number of synthetic pattern from there. That's the working principle. And now to fulfill this working principle, this is the algorithm. So in this case, this one is satisfied, and this sample, if we select this sample is not considered for further processing. So coming to the next one, now say this is the sample, and in our case we have chosen the value of M is 4, and this M can be chosen from the whole data set. It can be from minority region, it can be from majority region. So as this is the point, so now we find the 4 nearest neighbor. These are the nearest neighbor. This one, and this one, right? Now call this set as MP. Now calculate M0. M0 is talking about MP. In MP we are having which one? This, and this. Intersection L. L means what? Majority instances. So we have all those majority instances, right? They're black. So now if you find the intersection, there is only one black. Only one black. So now the value of M0 becomes 1. So if it is 1, the first case, M0 equals to M, this case is not satisfied. This case is not satisfied because the value of M0 is 1 and the value of M is 4. So this case is not satisfied here. Now coming here, if M0 greater than equals to which one? 0. 0 less or equals to this one, means this one is greater than or equals to equals to 0. So the value of this one is 1 and less or equals to M by 2. The value of M is 4 by 2. So 0 less or equals to 1 less or equals to 2 in this case. So in this case, this condition is satisfied. If this condition is satisfied, then what it said? It said that P is safe. Ignore P and continue to the next point. So if P occurs in such a situation and the event is like that, then again this P is not selected because P is now set. Now come with the third point. Here we have chosen a third point here. Here we have chosen a third point here. So this is the point now. No, sorry. Yeah, this is the point now. This is the point now. So if this is the point, we have to find M nearest neighbor. Before that is 4, MP4. If we find the value of M0, that's the intersection of MP and L. So as it's the intersection of MP and L, that's why the value of M0 now becomes 3. Value of M0 becomes 3 because in this MP we are having 3 black dots and 1 blue. And this set completely consists of all the black dots. So if you find the intersection, no doubt the value of M0 becomes 3 now. If it is 3, then this condition is not satisfied. This condition is also not satisfied because it's a 3 less or equals to 4 by 2. That is 2. 3 less or equals to 2. So the condition is not satisfied. So now here we are coming. So it's a 3. M by 2 means it's 2 less than 3 less than 4. Yes, if the value is 3, then this condition is satisfied. So if we have this kind of sample, then this sample satisfies this condition. As this condition is satisfied by this sample, that's why P is now, is said what? Add P to the danger. Now P has to be stored in danger. Danger is a set of such kind of samples. Danger is a point of such kind of sample. Now what is the sixth number? For each sample in danger, for each point D in danger, apply the smooth algorithm to generate the synthetic example. Now means what? Again we have to apply the smooth algorithm to create the synthetic examples, but now we have to apply this smooth algorithm to the set danger only. Fine. So if the oversampling algorithm is working in that way, then we can say that is borderline smooth 1. So again, we have a tunable parameter here. That is the imbalance ratio. You can give 0.5 or something else here. So we have a one more version that is called smooth 2. It's smooth 2. Initially, whichever we have discussed here, that is borderline smooth 1. Now we are coming to the second version. What is said actually? Read the line, then you can understand very easily. Borderline smooth 2 is similar to borderline smooth 1, except in the last step. In the last step, the new synthetic examples are created along lining joining points in danger to either their nearest neighbor in S or their nearest neighbor in L. Because in case of smooth, whenever we are finding the nearest neighbor to create the synthetic patterns, all the nearest neighbors should be created from the minority region, means smaller region. But if you try to understand, in this case, we can select either a smaller region or major, means larger region. Either we can take minority region or the majority region. So what we need to do, for an example here, this is the point. Now for this point, we need to create the samples. So looking here, we are having one sample here, which is lying to one neighbor, which is lying in the S, means the minority instance. So if our objective is to create only the data samples from the minority region, then the smooth should be applied here only, only here. This is the one case. And if we want, you again, I'm just telling one thing, just for your understanding, we have created one decision boundary. But when we are treating class imbalance problem, then there is no classifier, no trained classifier, no boundary is there. Try to understand. To make you understand, only this boundary is given. So in the first case, we can create the synthetic pattern. In this case, in such a situation, if we choose the minority region only, then the patterns can be created or smooth can be applied here only. But another case is there. The second case is what? We can create the synthetic pattern also from the majority instances or from the majority region. So either from minority region or from majority region. So if you want to create the synthetic pattern from the majority region, then we have to create synthetic pattern here in this case as well. So in case of mode 2, we have two ways. Either we can create the synthetic pattern from the minority region or from the majority region. That's the difference between borderline is mode 1 and borderline is mode 2. Because in case of borderline is mode 1, all the synthetic patterns should be created from minority region, because that's the working principle of mode. So up to here, we're having many here. I think possibly, yeah, then a combination, addison is there, but I did not include all those things here. So one thing more, we have oversampling, we have undersampling. One thing somebody can do whenever we do research or we do experimentation, both can be combined. So some of the part we are doing oversampling, for some of the part we are doing undersampling. So here one of the combination we're showing here. So sometimes actually whenever we combine both methods together, the accuracy of the classifier becomes higher. So in this case, see here, we apply small plus stomach lean. So this is the size of the large. This is the size of the small. So size is 680, and here the size is 6320. So highly imbalanced data set is highly imbalanced data set. In such a case, what we can do initially, we can apply here the undersampling. So if we apply the undersampling here, then automatically we can reduce some of the patterns from here. So we reduced it and made it 6050, and here we applied oversampling, and here we made it 3160. So somehow now we made the balanceness using oversampling and undersampling together. Similarly, here is another option of the experimentation. Similarly, we can do different kind of things, different kind of combinations to make both undersampling and oversampling together to improve the performance of the classifier. In case of machine learning, the objective is to learn, and if you want to, and the objective is learn to solve the problem. But the main objective, when the designer design one model, the objective is that the accuracy, the model will perform 100%. So you try to understand whenever we have a non-linear data set, it's not possible to achieve 100%. But then we try to optimize the accuracy close to 100%. So for that reason, we do different kind of data processing or data preparation. We apply different kind of data preparation technique there. So after that, we are having here, this is the algorithmic approach, not going to discuss an ensemble approach. After that, we are having feature analysis. In feature analysis, we are having a different kind of thing, right? What is feature extraction algorithm, feature selection algorithm, which all kind of algorithms are there and different kind of things are there. So next day we'll see all those things. Today we'll do the hands-on practical with all those class imbalance problem. And we are looking that if the data set is really imbalanced, then how, if we apply sampling techniques, how the accuracy can be improved. So also we can apply algorithmic level solution, but you try to understand here in the experimentation, I have taken only the sampling approaches, oversampling and undersampling approaches to show you the performance whenever we apply those kind of techniques in some imbalanced data set. So now going to the experimentation. So treatment of class imbalance problem here. So initially we're going to do random oversampling. So going to apply the random oversampling. Before that, I'm just trying to show you here the number of samples here. How many samples are here? Already we have seen the thyroid data set, and that is imbalanced in nature. But now I want to calculate, you can calculate here. So already we have pandas is already available, right? Now we call which data set? This is a thyroid data set. And where in constant F1. Now we want to see how many classes are different classes are there. This is one of the function by which we can calculate the different attributes in a particular data frame. So here we have taken the columns, the data frame is class, this one. Fine, because this data set already we have seen, I think. I can show you, no problem. So initially, just I'm deleting this one, finding the columns here. Columns here. So now we are invoking F1, So looking the name of the columns here. So columns here running, the columns are like that. So these are the columns, right? 1, 2, 3, 4, 5, this one, and a class is another column. So class is the classification. So here you can see more clearly, if we make like that, F1, here see the data set. So we have a 1, 2, 3, 4, 5, 5 independent variables, 5 say you can say attributes, and one a class level this. Now we are interested to see the class level, whether that is class imbalance problem or not. So looking this one, using this function, we can count the different attribute values. We can count the different attribute values using which one? Value counts. These value counts is available in pandas library function. Whenever you apply value counts, so to a particular data frame, then you can understand how many discrete values are there in how many frequencies. So now if you run here, then you can see the output simply running or not. Running, see here, 0 class is 359 and 1 class is how many? 69. So already when we did the data visualization, I have shown you the histogram of this data set. And this data set is imbalanced data set. So now we are trying to apply the algorithm, so oversampling and algorithm, and try to find out the accuracy. So initially in this data set, without using any undersampling and oversampling technique, we are trying to find out the accuracy. How much is the accuracy? Looking on that, find the data set is already invoked in F1. Right? So now apply the decision tree, looking how much is the accuracy. If we don't use any kind of undersampling and oversampling technique, then looking how much is the accuracy. Now you try to understand this file is available with F1. Now we have a F1 and F1 is having the whole data set. We didn't do any sort of sampling kind of thing or any kind of treatment for imbalance data. We didn't do anything here. So now we have the whole data in F1. Now apply the decision tree and looking how much is the accuracy. So in this case, that we have taken the test set that is 20% and we kept 80% for training. You can change it. Looking how much is the accuracy. Not coming while. How much is the accuracy? Yeah, the accuracy is if you don't apply any kind of oversampling and undersampling technique, then we're looking at the accuracy is 0.97%. So again, I'm telling one thing, it's a highly imbalanced data set, but still the accuracy is 97%. It means what? It means the data set is, or the problem is not highly nonlinear problem. It's a bit of linear problem. So whenever we have a bit of linear problem, then automatically whichever classifier you can apply, it will give you around 100% accuracy. Fine. So that's why it is giving 0.97% accuracy. So, but looking here, that can we improve the accuracy? Even if the problem is not highly nonlinear, there is a bit of linear, but still we are going to see whether can you improve the result if we apply some undersampling or oversampling technique here. So already we have seen the accuracy. Now the random oversampling 1:1 means we are going to make equal number of 1:1 means what? We are going to make equal numbers of minority and majority instances here. So as it is oversampling technique, that's why it enhances the number of minority instances. So it will enhance the minority instances up to 359 because the majority instances, number of majority instances is 359. So looking here now, initially we're doing the experimentation here, and now we have kept in F2, F2. Fine. So now we did this experimentation, then you can see how much is the weight. Say initially. So should I do one by one? It's better to do one by one so that you can understand, right? So here we have done, cut it. So here we found here that how many majority and minority instances are there? Majority 357 and minority is only 69. So that is printed out by this function only. Okay. Now what we're doing, we have here. So not sorry. So here, just here we invoke the random oversampling. For random oversampling, we have to call one sub module that is called random oversampling. So as we are doing random oversampling, so if we don't have random this undersampling, there is no problem here. Similarly, if we have don't, because we are taking the data set from one of the existing folder, so there is no problem, no problem. So we are invoking here just submodule random oversampling, and here we have which one, random oversampling. So if we don't give anything here, any parameters, by default it takes 1:1. The ratio is 1. 1:1 means the ratio is 1. Means we are going to make equal number of majority instances and minority instances. Now this function, the whole one program is written here. This is a function. So this function is invoked in where it is invoked in ROS. Now in ROS, this ROS, right? And what we have done, we discarded the data set here. We have broken into two parts. One is the independent variable here, and here we have a dependent variable. Means here we have an input parameters, and here we have an output parameter, that is the class level. Okay, so we are printing here x. X means what? We are going to print only the input variables, with the attributes only. We are not printing here the class levels. Try to understand, because already we have discussed about this one. Because in case of this thyroid data set, we are having how many? We are having 6. We are having 6 attributes, 5 input attributes and 1 output attributes. One is the class level. So the input attributes has to be assigned in that way. Already we have discussed this slicing part, ILOC, how to do. Using this ILOC part, already the function is discussed. I should not discuss again. This part is assigned to X, and the class part is assigned to Y only. Now we are printing X, looking whether it is working or not. It's invalid. Where is the invalid? Syntax invalid. Where is the syntax invalid? Invalid sequence. Invalid. From sklan. I didn't write from sklan. From sklan, I cut it. I cut from sklan. Wait from sklan. I cut sklan from sklan. Oh, count this one I didn't do. Okay, fine. I'm giving whole part here. Initially giving whole part, not discarding anything. Copy up to here. Copy here. The same thing up to X we are doing now. Okay. Yeah, that's the accuracy now. Sklan has to be invoked. That was the mistake. Sklan. So here we printed out which one? X. X is the input variable. So input is this, and this is the input. Now if want to see the output is one here, Y. So I can put here Y, one by one doing. So Y is kept here. So now we can see the output. The output is here. You can see this is the class level. This is the class level. This is the class level. Try to understand, right? And now you can see this is the class level, and the training part is done here. And now here we resample it. We resample XY. Then you can see the shape of the resampling here. So here now the training is done. The training is done for the class imbalance, to sort out the class imbalance problem. So random undersampling, this function is stored in ROS. So we have here ROS dot fit resample. Fit, now fitting resampling is done here, right? So we didn't write anything, any value here. It means 1%. The ratio would be 1. So now that part, now if you want to see the total number of labels, Y labels, then we can find total number of Y labels. This means here we have seen the Y, we use a different function here. Try to understand. The same thing is done here using a different function. Just I have used here different function. Same thing can be done here also with the same function, right? So now we are looking how many are there. So now you can see the data sample becomes 0 type, 0 instance, 0 type class is 357, and one class is also 357 after sampling. Before sampling, you can see here the value. Before sampling, the class 1 was 69 and class 0 was 359. But after doing the oversampling, see here, this minority class now becomes 359. So now we have an equal number of both classes. Now we can say the database is balanced database. Fine. Now finally, using this function, the database is now stored. Final database is stored now in F2. So here we have a final database in F2. Looking, final database is stored in F2. Fine. So that's finally you can see the final database, right? This is stored in F2 now. So now we are using the decision tree to see whether the performance is increased or not. This is without oversampling. The with oversampling here, this code is here. With oversampling, what we change only? We change only the file name, because now the oversample data set or the sample data set is stored in variable F2. So in earlier, the decision tree was applied here, but we applied the file name that is F1, because in F1 we have the initial data set without doing any sampling, without doing any kind of treatment of class imbalance. So that one is done here earlier. But now the treatment is done, class imbalance the treatment for the class imbalance is done. After doing the treatment, the data set is stored now in F2, in variable F2. So in this decision tree, just we change the variable name or the data set name, and here we have the data set that is F2, F2. And now we train and finding the accuracy here. The accuracy becomes 99%. So whenever we change, whenever we have done here, the oversampling kind of thing, that we're looking that the accuracy is improved, and here it becomes 99%. Okay, so now I'm just trying to change it by which one? If the ratio is changed only, the ratio is changed to 50% only. Doing the same thing, how we can change the ratio? Simply by writing this one. So here, if you don't write anything, it means what? If you don't write anything, it means that we are trying to make the ratio 1. Means we are trying to make equal numbers of oversampling data and equal number of, say, majority instance and equal number of minority instance. But now if our objective is to make the ratio 50%, then we need to write this one simply. The sampling, this is called what? Sampling strategy equals to 0.5. Now our objective is to make 0.5. Looking here, if it is 0.5 means what? We are reducing half of the. We have reduced. It means the majority instance would be double of the minority instances. So see here, we have done this one, and finally see how many minority and majority. Here you can see the minority and majority. So majority is 359, and now the minority becomes 179. So now the sample of minority instance is 50% of the majority instance. Whenever we give this one, this is the ratio. You can change the ratio, and this ratio is also the tunable ratio. Whenever you tune, then automatically the accuracy will be changed. So if we did this kind of, say it's 0.5%, then what happens looking on that? So already run on not, yeah, we have run here. So we have run here, now looking. So after running this one, all the reflections are made in F2. Just to have changed this one, and already it is executed. So now reflection is on F2. Now F2 will be used in decision tree, and already F2 is here. Now we are running this code, looking how much is the accuracy. So now the accuracy is dropped. Accuracy decreases. It becomes 98% now, but still it is better than without putting any oversampling techniques there. Because without putting oversampling techniques, the accuracy was around 97%. So whenever this oversampling technique is applied and the ratio becomes 0.5, now got the accuracy that is 98%. Done. This is 98%. So now we are going to apply one more technique here. That's already we have discussed about which one, smooth. So coming smooth, initially you're doing oversampling. Even though we discussed about undersampling first, but we are doing the oversampling here, the experimentation. So no problem here. So looking here, we're taking the smooth now. We are going to run now the smooth. So whenever we want to execute smooth, then we need to execute one more submodule that is smooth. That is called smooth. This is the submodule, and this submodule is available in this package. The imbalance.oversample. Here, this submodule is available. Fine. So random undersampling is not required here. We're cutting random undersampling from here. The bottom line, smooth is also not required because we are doing only the smooth. Fine. And now the function of the smooth is like that. So whenever we are not specifying within the bracket, means we are not passing any argument to this function, it means that the ratio becomes 1. The same thing we have done. The rest of the thing is same, just we have changed here the oversampling technique name. Here we have applied smooth, and in that way smooth can be applied. Now the smooth is invoked in over. The over is given to resample x and y here. Fine. So now we are running here. So here initially we had how many? 0 level 357, 1 level 69. After doing the resampling, 0 level becomes 359. There is no change, but this minority minority instances are increased, and it became now 359 equal because the ratio is 1, because it didn't specify anything here. So if nothing is specified here, then automatically the ratio become 1. So now the whole reflection is made where? In F3. If we have written here the file name that is F3, or it's a variable. Now the resample data is stored in a variable that is F3. And now we're running in F3, looking how much is the accuracy. F3 with the DT. So here we have the decision tree, looking the accuracy here. Looking the accuracy. We are running here and we have F3. Okay. So looking the accuracy here. So whenever it becomes 0.5, the ratio becomes 0.5. Now not 0.5. This ratio is 1. Ratio is 1 in smooth. The accuracy is 99%. Accuracy is 99%. So now changing the ratio here, just changing, and the ratio becomes say 0.5. So if the ratio will change, looking how much the accuracy changes here. Now in smooth, just we change. What do we change? I'm not deleting. Many of the things can be deleted here, so I'm not deleting any one of them. So here, just we are making the ratio 0.5. Already know how to do that one. Sampling strategy equals to 0.5. So now we apply the smooth, and the ratio we kept here 0.5. Running this one. So 0.5 means what? The minority instance becomes half of the majority. So here see, the majority is how many? 357, and minority 179. And the final resample data is stored in F3. Now we are applying here with the DT. There is no change in the DT, same DT. So the same DT here, we have a same DT. So looking, this is the, now if the same DT, yeah, F3 is same, then why this? Yeah, accuracy is this then. Is here 53, yeah, 5%, and it is doing, it is stored in F3. Sample is like that. Total number of sample is this 538, and same F3, there is no change of F3. Yeah, if we apply this one, so the accuracy 99, there is no change. I think the same. If we make it 0, yeah, same. I think there is no change. No change. Yeah, there is a bit change. I think there is a bit change here. See, when it was 100%, means the 1, the ratio is 1, 99.30, and here 99. See here 99.07. See, a bit change is there, right? So there is no big change in this database. It doesn't mean that this would be uniformly applicable for all the data set. I told you already, all things, all the output depends on nature of the data set, nature of the data, whether the problem is highly nonlinear or the problem is linear. If the problem is linear, then it can be done very easily. It can be sorted out very easily, right? Even if we don't do any kind of, say, oversampling and undersampling, even if the imbalance ratio was high, but still it was producing 97% accuracy. It means what? The problem itself is a bit of linear problem. It is not highly nonlinear problem. So whenever the problem becomes highly nonlinear, and whenever the impact of imbalance ratio or imbalance, class imbalance problem would be high in a data set, so in that situation, if we apply any technique for class imbalance problem to sort out the problem of class imbalance problem, then automatically we can see that there can be a huge difference or huge improvement in accuracies. So it depends on different data sets. Fine. So you can do different kind of analysis, taking different kind of methods, different kind of techniques, using different kind of data sets. So all the data set you can get from, say, UCI repository, Kaggle data set, you can get. Those are the standard data set you can use, and you can do the experimentation, and you can get certain kind of conclusions on that. Thank you, everybody. Any questions? Any question? Next, you can, yeah, see that one thing, it doesn't mean that we don't have a classifiers. We have all the machine learning classifier, but we are coming one by one, right? So after that, we'll have this on which one. Here we have a feature selection, then we have data normalization. Then we are going to discuss about different kind of classifier, decision tree, random forest, KNN, then name base, right? Support vector machine I have, but I did not include in this slide. So till that, we have only discussed about 84, but I intended to discuss about 257. So it's not possible because I'm going very slow. And you told me to go slow, that's I'm going slow, right? So we have to know.
Any good textbook that you would like to suggest for the beginners?
So madam, that's why I intended to circulate you at last the PPT, because in the PPT I have to give all the references, because I have many references, not from a single book, many references. So I'll put all the references in the final PPT.
Okay, sir. Thank you. Participants, do you have any doubts? Please ask your doubts.
Possibly there is no question. Thank you. If you are having any question, make it. So put relevant question in the next class. When we'll start, you can put the question. Because today we have did the experimentation with only oversampling, and next day we'll do 1, 2, 3 experiments using undersampling. Then see the impact of undersampling. If the size of the data set is small, then what is the impact of oversampling and undersampling? You can do the experimentation yourself also, but here we'll do the analysis. Just we have done here only oversampling, and we have seen the accuracy. Thank you, everybody. Thank you. Thank you.
Thank you so much, sir. Thank you so much for joining. And thank you so much for your valuable session. Thank you so much. Shall I stop the session for today, sir?
Yeah.
Thank you so much.